Jnanam paramam dheyam. Knowledge is supreme.
So, I tried to give you enough motivation in the last lecture that for L equal to 0, the Zeeman splitting should not be seen, but L equal to 0 you still see two close, very close lines in the lab or in the experiments, and you cannot account if you live only with orbital quantum number L and ML, the magnetic quantum number ML. It is not possible to account for L equal to 0 having two distinct lines showing up in the experiments. So, the only way out is that there is an additional quantum number which is the spin quantum number. This is put by hand as far as non-relativistic quantum mechanics is concerned. There is no formal way in which, because of the experiments, in order to understand the experiments and that there are exactly two lines for L equal to 0, you are forced to put in a spin quantum number for the hydrogen atom, which is S equal to half. So, this is in addition to the three quantum numbers which you had, which is N principal quantum number, L azimuthal quantum number, and ML which is the magnetic quantum number. Okay. I am sure even in the middle of the sleep, when you are trying to see the periodic table, you know what each of these quantum numbers are, and we see from the Schrodinger equation that these three quantum numbers are essential for the wave function. See, when we wrote this position space wave function in one dimension, we said that we take the state psi and take the projection with respect to x, right. So, this is what we said as a position space wave function, where this is the Dirac state of a system. When I write psi n l m, which is function of r theta phi, how do we do this? Okay, so suppose I had an n here, you could have put in an n here for particle in a box. N is the nth excited level of the particle in a box. N equal to 1 is the ground state, n equal to 2 is the first excited state, and so on for the particle number. This I am assuming that all of you are. Now, the hydrogen atom spectrum, we found that this is the solution. So, there is a neat way in which you can write this as if, what do? You can take r theta phi and take it with n, l and m, or I could put a psi subscript, but both are equivalent. You can forget about the psi and write an n there, okay, but you can write it. What further? You can also write this as r with n, yeah. So, the theta and phi is basically giving you the unit vector direction. Suppose you have in 3 dimension, if I put a unit vector, some unit vector, that tells me what is the theta and phi. You all agree? So, you could try to split this and write it as if it is r times n, and I can put an unit vector whose magnitude is this radial value, but whose direction is giving you the angle theta and phi with Lm. What is this we are going to call? We are going to call it as the radial part of the wave function. What is this? This is your spherical harmonic, which you can write it as Ylm of theta phi, or you can also call it as hat n vector, where hat n is a unit vector. That's true. So, it's not, it's I should say it is approximately, I should keep in the back of my mind that there is this L dependence which is there. Okay, so this is correct. This one has to be taken that there is a L dependence here in this space. Good point. Okay, so let me put that also here just for us to remember. So this we don't know offhand, but because we know the solution, we know this is the way. What else did we do? We also said there is a L hat squared operator on psi n L m r theta phi. What was that? L into L plus 1 h cross squared psi n L m r theta phi. If suppose we use that definition, it operates on position or on this. The quantum number seems to pick up the, like if you had the energy operator here, it does not operate on the position basis. It operates on this and gives you En times psi. So similarly here what will you say? From here we could try and say L squared on NLM will be so the Dirac notation is coming into play, that whenever we write the quantum state as a ket vector, we can try to denote it by the 3 quantum numbers NLM, and it is an eigenstate of L squared with eigenvalue L into L plus 1 h cross squared. And similarly, what happens to LZ? What happens to LZ? Is it an eigenstate? So we saw LZ is minus IH cross del by del phi, and you can write LZ on psi NLM r theta phi to be MH cross psi NLM r theta phi. This was the data which we studied in the last lecture. We introduced orbital magnetic moment, and I explicitly said del by del phi will operate only on the e to the im phi. I will give you the m phi, right? H cross is coming because you put a position representation for LZ, which is r cross p, where p has a minus IH cross del by del. That's why that H cross is coming. So now in the Dirac notation, can I write this? Is it an eigenstate with eigenvalue? MH. So what have we seen? Hamiltonian on NLM will give you NLM. So the energy eigenvalue is independent of the other 2 quantum numbers, and we also see the same state is an eigenstate of LZ. If you have simultaneous eigenstates, should also be complete. Okay, some 2 states matching doesn't mean that it will be simultaneous eigenstate. When I say it is complete, how do I write this completeness relation? Summation over NLM NLM with the appropriate summations, all possible n's going from 1 to infinity, L going from 0 to n minus 1, m going from minus L to plus L, that constraint thing which you have to put in here. Completeness condition tells you that it should be identity. So if this is valid for all the states, it is true for any arbitrary state I have written. What can you compare from here? What can you say? Are they compatible or not compatible? They are compatible observables. Hamiltonian commutes with LZ and they share the simultaneous eigenstates. It's a simultaneous eigenstate of both LZ, the complete set, both LZ and H, Hamiltonian. Conversely, you can say that the Hamiltonian commutes with LZ. We have seen all these things in the rotationally invariant central potential problems, but I am just trying to put it in a notation where I will slowly take you on to the spin quantum number and how to go about doing this Dirac notation from this picture. Okay. What about L squared? L squared also satisfies this, right? Which was what we saw in the earlier transparency. So can I also say L squared is actually L dot L, the operator form of L dot L. They also share the simultaneous complete set. So this will be 0. What about H with Lx? We did this for Z. But if you want to do Hamiltonian with Lx, that will also be 0. But will this be an eigenstate of Lx? Why? Lx Lz is not 0. You can either write eigenstate of Lz or you can write eigenstate of Lx. You cannot write a simultaneous eigenstate of Lx and Lz. Right? So you need to find from this set, even though H with Lx is also 0, what is the set which is compatible if I ask you, the total set? You have to find the intersections. What is the intersection possible given this data? It's not an eigenstate of Lx. Everybody agrees, no? You can go and check and see that it's not an eigenstate. So it's a simultaneous eigenstate of Hamiltonian, Lz and L squared. So that is the maximal compatible set you can write. You can't look at all the commutators and say Lx is also compatible, Lz is also compatible. You can't say. If you say that, you have to also make sure Lx, Lz is compatible, which is not. So only one of the two should be taken into consideration, either Lz or Lx. And we conventionally take Lz to be the conventional axis, z axis, to be the simultaneous axis. Okay. So maximal compatible set will be Hamiltonian, L dot L and Lz. That's it. Even though Hamiltonian commutes with Lx, Lz don't commute. So it cannot be a simultaneous eigenstate. Here the state which I write NLM is a simultaneous eigenstate of Hamiltonian, L dot L and Lz. Clear? So this is the way to go about. Either you can see a compatible observables, write the simultaneous states, or conversely, since I have found these states and I have explicitly verified to be an eigenvalue equation, I am trying to argue for you that for central potentials, Hamiltonian commutes with all the components of angular momentum, but all the components of angular momentum don't commute amongst themselves. So the maximal compatible set which defines a simultaneous eigenstates, which is NLM, is a simultaneous eigenstate of H, L dot L and Lz. Clear? You can take projections here with hat n. And what will this be called? This will be Lz operator on the YLM part. Okay. So you can try to write Lz on YLM of hat n is MH cross YLM of hat n. And you can give a position representation for Lz, just like we did for the momentum, linear momentum, independently. You know what these functions are, and you can find what this satisfies, this equation, and you can say Lz, the position representation will be del by del phi in spherical polar coordinate. Okay. If you do a del by del phi on the spherical harmonics, you will get an MH cross. Is the connection getting clear to all of you? such a beautiful, elegant concept of Dirac formalism that you can throw away putting the projection onto the position coordinates and play around with the states as NLM in the hydrogen atom problem. But at the back of your mind, if you want to write what is the position operator for LZ, you can figure it out from here. If you are clear with this, then the rest of the Stern-Gerlach and all will be very, very smooth. You will understand it. They are all finite dimensional vector spaces. These NLM for a specific n. If you take a specific n, this LM, the degeneracy is n squared. Now, if you want to introduce spin quantum number, what do? I have to multiply, or if you can call it as ML, then you will have a, a separate space, internal space, which they call it as a tensor product or a Cartesian product. Like if you are in a line, one-dimensional line, we call the coordinate as x. If you are in a two-dimensional plane, you call it as x comma y as a point, right? But formally, when I write a state here, I would write it as x. When I write a state here, I would write it as x comma y. But you could also write it as x into y. No harm. It's the same thing. You have a space which is principal quantum number, azimuthal, magnetic quantum number. But you also have, you are forced by experiments to introduce a spin quantum number and MS quantum number, which is independent. And because you see two lines in the experiments, even for L equal to 0 in the presence of a magnetic field, we try and say that this is half and MS can take values plus or minus half. It goes from minus S to plus S. Is the motivation clear? How this S equal to half is pushed in from the experimental data? Because you have two splittings only seen, not more than two splittings. Yeah. So that is why. If you take S to be half, the magnetic quantum number corresponding to the spin quantum number will go from minus S to plus S in steps of 1, right? If this one should take from minus S plus 1 to plus S. And I want this to be only two states. There are only two lines splitting seen. What is the solution? S has to be half. You can work with arbitrary S also as a theory person, but then if you want to compare with what is happening in the lab, you need to make contact. And here for making the contact with all these Stern-Gerlach and the anomalous Zeeman effect seen, you have to have S equal to half. Yeah, just like your orbital quantum number, the properties of the spin quantum number is exactly similar to, this is ad hoc. In non-relativistic quantum mechanics, we are just saying that if you have an S and an MS, there is an SZ operator which will give me MS H cross SMS. Exactly like the orbital quantum number, I want my spin quantum number to be here. And also there are other kind of data like the spin orbit coupling data, which shows that these couplings cannot be done if you don't allow your spin operators SZ with SX to be exactly similar to the way the commutator bracket, it has to be similar to IH cross SY, exactly like your LZ LX. The commutator bracket of LX with LY, that property is kind of seen also for the spin quantum number. So you can't, it behaves exactly like the orbital quantum number as far as properties are concerned, but it's just that this quantum number is in a different space. There's no way you can make this behave differently if you try to do it. Like it's something similar to F equal to ma when I write. If left hand side is a vector, the right hand side has to be a vector, right? It's as tight as it is. The L quantum number, if I say the magnetic quantum number for ML goes from minus L to plus L, because there are spin orbit coupling, the S also should have a spin quantum number and MS has to go from minus S to plus S. That's it. Theory, you have no choice. Okay. But as far as non-relativistic quantum mechanics is concerned, This is the postulate for you. But if you do Dirac equation and relativistic quantum mechanics, these things comes automatically. This is what I was telling you, that if you try to do the Heisenberg's equation and do dLz operator by dz in your hydrogen atom or non-relativistic Schrodinger equation, it has to be proportional to commutator of Hamiltonian with Lz, so it has to be 0. But this is non-zero in relativistic quantum mechanics, because the H relativistic, which is the Dirac Hamiltonian with Lz, is non-zero. This you don't see in your Schrodinger equation. And the way to make for rotationally invariant angular momentum has to be conserved in relativistic theory. If you introduce another SZ operator, this is also not 0, but you can show that the sum of Lz plus Sz, okay, you can show that d by dt of Lz plus Sz, which you will call it as the total angular momentum, this will be 0. Okay, so this requires relativistic quantum mechanics, and you can show the properties of Lz and Sz are exactly how its commutator behavior with its components, how its commutator behavior with other components in that space. But these two are two different space. What do I mean by two different space? Suppose you want to compare bananas and apples. There's no way you can compare. Amongst them you can compare. So it's like Lz with Sz or Sx. You just put it to be 0. They don't have any connection. That's why you say it's a different space. Any components. I have written it for Z and X. But the L space and the S space are two different spaces. I'm slowly driving the fact that the spin quantum number is important, but it is not derivable from non-relativistic Schrodinger equation. But because of the experiment, we will put it by postulate that there is a spin quantum number S and Ms, which is, you can take it as a Cartesian product or a tensor product, and you can do spin operators on those states. So this is why the motivation which forces your S equal to half and the corresponding magnetic quantum number. And we just looked at an electron in a 1/r potential here, right?